calculating atomic mass and using moles in our calculations. And you can go to your notebook and see that on page 86. But today I wanted to walk you through some of the practice problems we did in class. So I'm going to rotate around in class. Here's what you saw at each station. There was a practice problem, and then there was an example problem worked out. So I want to go through and work on this and help you understand how we got here. So I've got a paper for each of these. But take a look at this example problem. The question is, what is glucose's molecular weight? Well, if we want to calculate molecular weight, we figure out what is the atomic mass for each of these, and you can go to the periodic table and look that up. If you go to the periodic table and look at carbon, you'll see this number there. And that's its molecular, or its atomic mass. We multiply that by how many atoms there are in the molecule, so 12.01 times 8. For hydrogen, the atomic mass is 1.01, and there are 18 of those in octane. Multiply those, add them all together, and we get the molecular weight of octane. That is, how much does one molecule of octane weigh in atomic mass units, or how many grams does 1 mole of octane weigh? And remember, moles is 6.022 times 10 to the 23rd molecules of octane. That would be 1 mole of octane. So that's how much it weighs. The next question is, how many moles of octane are in 26.2 grams? Well, we use our molecular weight to convert from grams to moles, and that tells us we have 0.229 moles of octane. The next question asks, how many atoms are in 26.2 grams of octane? Well, we already converted grams to moles. Now we're going to convert from moles to atoms. And this ratio is always the same. In 1 mole of anything, there are 6.022 times 10 to the 23rd of that thing. So if I had 1 mole of donuts, I would have 6.022 times 10 to the 23rd power donuts. That's a lot of donuts. And so we find that there are 1.38 times 10 to the 23rd atoms. I'm sorry, that should say molecules. Molecules of octane in 26.2 grams of octane. Technically, since this said atoms, gosh, maybe I need to multiply each of those molecules times 8 plus 18 to figure out how many individual atoms, but that should say molecules. So let's work through the questions about glucose. All right, so our first question says, what is glucose's molecular weight? And on a summative, I would give you that glucose is C6H12O6. That's not one of the ones you need to memorize. Really, you only need to memorize oxygen gas is O2, water is H2O, carbon dioxide is CO2, things like that. But let's do the molecular weight. So we have 3 different elements here. We've got carbon, let's speed this a little bit, carbon, hydrogen, and oxygen. Okay, and we know that there are 6 carbons, 12 hydrogens, and 6 oxygens. So if you go to your periodic table, you can figure out how much a mole of each one of these elements weighs. Carbon weighs 12.01 grams for each mole, for each 6.022 times 10 to the 23rd atoms of carbon. Hydrogen weighs 1.01 grams per mole, and oxygen weighs 16.00 grams per mole. Okay, if we do the math for each one of these, 6 times 12.01 gives us 72.06 grams per mole, grams of carbon in 1 mole of glucose. We have 12.12 grams of hydrogen in each mole of glucose. And we have 96.00 grams of oxygen in each mole of glucose. If we add those all together, overall, we see that C6H12O6 weighs 180.18 grams for each mole of atoms we have of it. So that is its molecular weight, or molar mass. That's another way to say it. Okay, so there's our molecular weight. So next, it asks, all right, what if I have 26.2 grams of glucose? So I have 26.2 grams of C6H12O6. That's my given information. Well, this is just a unit conversion. I'm going to go from grams to moles, And this right here is my conversion. 180.18 grams is equal to 1 mole of glucose. So if we've got grams up here, then in our next chunk of math, we're going to have grams down here, and it's grams of C6H12O6 still. We know that 180.18 grams is equal to 1 mole of C6H12O6. Cancel out our units, we're left with moles, so we did this right. And that's going to be 26.2 divided by 180.18, and that gives us 0.145 moles of C6H12O6 in 26.2 grams. So this is kind of like saying, how many molecules of glucose are there in this weight of glucose? And the answer is 0.145 moles. Okay. Remember, a mole is like a dozen or a pair. All right, it's a number. So not quite a full mole here. Our next question is, how many atoms are there? Okay, well, in this case, we're going to have to go grams to moles to atoms. Okay, now we already went grams to moles, so we can actually just start with this number right here. We know we have 0.145 moles of glucose. And we know that any 1 mole of something, it could be donuts, it could be glucose molecules, it could be moles like the animal, is 6.022 times 10 to the 23rd of that thing. So in this case, it's molecules. Okay. Do our math, and we get 0.88 times 10 to the 23. This shouldn't be atoms, this should be molecules, because glucose is not an atom, it's a molecule. All right, so that's how many molecules of glucose we have in that many grams. However, this is not good scientific notation, so we're going to move this decimal place one, and that gives us for a final answer of 8.8 times 10 to the 22nd molecules of glucose. And I apologize, I asked atom here. If I actually wanted to figure out atom, well, how many atoms are there? 6 plus 12 plus 6, I could multiply that by this, and that would give me actually how many atoms are there in glucose, but there's no such thing as an atom of glucose. Glucose is a molecule. Okay. So, if I have, it's about a cup of sugar. In a cup of sugar, there are about 8.8 times 10 to the 22 molecules of glucose. That's pretty cool. So that's our first question, first set of questions. And that, now that we've learned about moles, you'll see that moles start showing up kind of everywhere. So our next question is about unit conversions and gas laws. If you need some help on these, take a look at pages 66 and 67. But here's our questions. We're being asked, what's oxygen's molecular weight? How about water? And there's an example over here of how to calculate molecular weight. They calculated molecular weight for carbon dioxide. And then once you know the molecular weight, let's say that much gas is released. Okay, it's about this many grams. How many moles is that? Okay, we can go grams to moles, just like we did on the last problem. And then finally, how much space will that fill? Well, if this is a gas, we can go back to our gas laws. Pressure times volume equals the amount of substance. That is moles times our gas constant times temperature. Okay, plug that all in, solve for volume, that's this. And that gives us 22.03 liters of carbon dioxide. So let's do the actual practice problem together. Here we go. What is oxygen? O2. Oxygen gas is always O2. What is oxygen's molecular weight? What about water's molecular weight? All right. Well, let's do oxygen first. So we're going to do O2 right here, and we'll do H2O over here. Okay. Well, oxygen only has one element. It's oxygen. How many atoms of oxygen are in O2? Well, there's 2 of them. If you look at your periodic table, you'll see that each mole of oxygen weighs 16.00 grams per mole. Okay, well, 2 times 16 is 32.00 grams per mole. Okay, so that's one answer. That's the answer to the molecular weight. Another way of saying that is molar mass of oxygen. How about H2O? Well, we can do that too. There's two elements in here, oxygen and hydrogen. We see one oxygen and two hydrogens. Each oxygen still weighs 16.00, and each hydrogen weighs 1.01. That's in grams per mole. I'll never forget your units. 1 times 16 plus 2 times 1.01 is equal to 18.02 grams per mole. That's the molecular weight of water. All right, so we've got our molecular weight, molar mass, same thing for oxygen and hydrogen, or excuse me, for oxygen gas and water. It's water vapor. It's the same thing. So our next question is, how many moles of gas are released in total if hydrogen peroxide breaks down to form 64.8 grams of water vapor and 79.2 grams of O2? All right, let's see. It doesn't look like hydrogen peroxide matters because it's breaking down. What matters is water vapor and O2. So let's say we've got this many grams of water and this many grams of O2. It looks like we're going to do two problems and then maybe add them together to see how many moles of gas are released total. So let's start with oxygen. If we're starting with oxygen, they told us we have 79.2 grams of oxygen, and we're going to convert grams to moles using our handy dandy molar mass right here. We know that every 32 grams of oxygen we have is 1 mole of oxygen. This is a unit conversion like we've done previously. So 79.2 divided by 32 gives us 2.48 moles of O2. All right, so it's going to be 2.48 moles of gas over here. But we also have to think about the water vapor. So water vapor is just water. There were 64.8 grams of it. That's what our problem said. And we need to convert that to moles. Well, once again, we've got our conversion right here. For each 18.02 grams of H2O, we have 1 mole of H2O. And see, just like these units canceled out up here, grams of H2O cancel out, and we're left with moles of H2O. And that's going to be 3.60 moles of H2O. So come on over here, 2.48 plus 3.60 equals 6.08, there we go. 08 moles, sorry, I rounded differently. Moles of gas total. Right, that's how many moles of gas we have. That's 6.08 times 6.022 times 10 to the 22 molecules of gas. Now, the next question asks, what will the pressure of that mixture of gases, the water vapor and the oxygen gas, be at sea level and 20 degrees Celsius if it's confined to a room? So let's say we had a jug of hydrogen peroxide, it broke down into water vapor and oxygen, and it's stuck in this room. What's the pressure in that room going to be? Well, first, we never do degrees Celsius. So first let's convert 20 degrees Celsius to Kelvin. That's 2 plus 273.15 degrees Kelvin. Okay, so that's going to be 293.15. That's the temperature we're looking at there. Okay, and that's about room temperature. Okay, I like to start with PV equals nRT. Let's see what we've got. Do we have a pressure? Yes. It says at sea level. Sea level means 1 atm. We don't have a volume. That's what they're asking. Do we have an amount of substance? Absolutely. That's what this was. So we've got that. We've already got our gas constant, and they did tell us the temperature. Okay, looks like we've got all of them. We're solving for volume. Okay. Oh, I'm sorry, we're solving for pressure. See, it said sea level, which makes me think it should be 1 atm. but it's actually asking about pressure. Okay, looks like I was wrong there. Looks like we're solving for pressure because they gave us volume. It's 450 liter room. Okay. So actually I probably need to get rid of the at sea level for next year. That's kind of confusing. So here we go. The pressure we don't know. We're at sea level, but the room may have been extra pressurized because of all the gas in there. We'll see. And the volume is 450 liters. That's how big the room is. And that is being filled with 6.08 moles of gas times our gas constant. Well, if we're doing pressure in ATMs, our gas constant is 0.0821, and that's liters times atmospheres over moles times Kelvin. This is just the gas constant that makes the math work. And all of that is going to be times 293.15 degrees Kelvin. Okay, so this is going to be 450x, that's our unknown. If I multiply all these together, I get 146.2, and actually the units are going to be liters times atmospheres, and this is liters if you remember, because these canceled out when I multiplied them together. Divide both sides by 450, and you get x, which is our amount of our pressure, and that is, let's see, the liters cancel out. We're left with pressure, good. And that is 0.325 atmospheres. So it's actually kind of a low pressure in that room. It's less than 1. Okay. All right, so that's how we can use the amount of substance that we figured out to figure out the pressure in a place. All right, if that room was empty before, like a total vacuum, zero pressure from the air, then if we add the gas, this is how much pressure will be in that room. All right. All right, what's next? Let's see. What about the molecular structure of glucose? We haven't talked about that in a while. So you can predict molecular structures. I suggest going back to pages 24 to 27 to remember how that works. And then from there, once you know the structure, you can figure out the bond enthalpy. So let's do this now. The molecular structure of glucose. Well, when I'm thinking molecular structures, I know that carbons are always connected to carbons. So I could do a carbon chain. However, do you notice? Well, let's just try to do a carbon chain. C, 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 C. Put my carbons in a chain. I've got 12 hydrogens, but I like to do hydrogen last because they can only form one bond, so they take up the leftover space. Let's do oxygen. Let's go 6 oxygens. Okay. Now, each of these oxygens needs to form 2 bonds because it has 2 unpaired valence electrons, and you can go back to your notebook on page 27 to see that. Carbon forms 4 bonds, so we need some extra bonds here. But first, let's put in our hydrogens. We know that we want bonds all of these places. Okay, so if we did that, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. That's too many. We've only got 12. Well, we could do some double bonds. We could make this a double bond right here. Get rid of that bond and that one. Now he's got 2. This one's got 4. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. That works out very nicely. That could be the molecular structure of glucose. However, there is another option. Glucose could be a ring of carbons. It could be carbon, 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 carbon. And each one of those could get an oxygen and a hydrogen off of it. And I would give you credit for either of these structures because I haven't taught you organic chemistry, so you wouldn't know how to figure that out. But we could put our hydrogens on the inside. Now all the carbons have 4 bonds, all the oxygens have 2, and all the hydrogens have 1. So once again, we've satisfied it. I would give you credit for either one of these, but the correct structure turns out to be this one. So how do I figure out bond enthalpy? Well, remember, bond enthalpy is just how much energy would you release if you built all these bonds, or how much energy would it take if you needed to break all those bonds. So we just need to first figure out what kind of bonds we have. We've got carbon to carbon. That's one kind of bond. So carbon to carbon. We've also got carbon to oxygen. Well, first let's see, how many carbon to carbon bonds do we have? Looks like 6. How many carbon to oxygen bonds? 6. How many oxygen to hydrogen bonds? Oh, 6. And how many carbon to hydrogen bonds? Oh, that's 6. You can turn to your notebook, find your bond energies, figure out how much energy is in each of these bonds. So carbon to carbon, 347 kilojoules per mole are released if we break that bond. Are absorbed to break that bond, or are released if we make that bond. For carbon to oxygen, it's 358 kilojoules per mole. Oxygen to hydrogen, it's 467 kilojoules per mole. Carbon to hydrogen is 413 kilojoules per mole. And this is all on the page where you have your bond energies. Do that math, add them all up, and that is the bond enthalpy for glucose. That would be how much energy would be released when we formed glucose from all these atoms, or how much energy it would take to break it down into atoms again. Okay, so 6 times this, plus 6 times this, plus 6 times this, plus 6 times this, that's the bond enthalpy. Okay, and what we're actually finding out here, see, moles is starting to show up all over the place. This is literally kilojoules per mole of glucose that is broken down. So if we didn't have a whole mole of glucose, we wouldn't get all this energy. If we had more than 1 mole of glucose, we would get more from this, and we could figure out how to do that. But that is stoichiometry, and I'll teach you that in the next unit. So there's moles showing up again. Let's see what else we've got here. Ooh, this last one asks you to balance equations. So this last one we had, what type of chemical reaction has taken place when hydrogen peroxide, H2O2, breaks down into water and oxygen gas? Well, we can figure this out. And then we can balance it, just like this one is balanced here. All right, and these are combustion reactions. This is the combustion of octane. You've got that in your notebook already. All right, so let's try to do this. Hydrogen peroxide, H2O2, breaks down to form water, which we know is H2O, and oxygen gas, which we know is O2. Okay, so what does this look like? Well, I see one thing breaking down into 2 things. That looks like a decomposition reaction. And you've got all the different types of reactions on page 74. Yeah, that looks like a decomposition reaction. Let's balance this. Okay, so I'm going to write it again right here. H2O2 breaks down and forms H2O plus O2. Okay, I see I've got hydrogen and oxygen on this side, and I've got hydrogen and oxygen on this side. Got 2 and 2 of each on that side. On this side, I've got 2 hydrogens and 3 oxygens. Oof. All right, well. That's a little tricky, isn't it? Well, first things first, let's do this. I want a nice round number of oxygens, so I'm going to put a 2 right here. That makes this 4 hydrogens, and that makes this 2 oxygens plus another 2 over here. It's going to be 4 oxygens. 4 and 4, 2 and 2. If I put a 2 over here, now we've got 4 of each of those. That's kind of a tricky one, but there it is. 2 hydrogen peroxide. This 2, you can think of this actually as 2 moles. 2 moles of hydrogen peroxide breaks down to make 2 moles of water, and remember there's an invisible 1 here, 1 mole of oxygen gas. Whenever you read one of these equations, you can read it as 2 moles of hydrogen peroxide breaks down to form 2 moles of water and 1 mole of oxygen gas. So connecting all these things together, I could ask you, now that we've got our 1 mole of oxygen gas and 2 moles of water, how many moles of gas does that produce total? It would be 3 moles. Okay, what's the pressure given this space? All of these problems can connect together. So there you go, that's how I would work these problems. You got a lot of practice in your notebook. Finish up your homework problems. Come see me in IEP if you need help. You got answers at the bottom. Yeah, get the help you need. Your summative is coming up.